Hey, welcome back. It's True again with another phytech development video. Today we're going to be looking at graphics, specifically embedded wizard graphics on the phyCORE-i.MX 8M+ development kit. Let's get into it. In order to work with embedded wizard, we're going to need both a Windows host environment and a Linux host environment. So to achieve that today, here I have a Ubuntu 20.04 virtual machine hosted with VirtualBox, and then I have my underlying Windows host, which is native to my workstation here. And so you're going to want to emulate this setup in order to follow the instructions in this video. The reason that this is necessary is because phytech's Linux BSP is only supported in Linux host environments. Specifically, we have validated the PD24.1.0 BSP with Ubuntu 20.04. So you're going to want that. And then the Embedded Wizard Studio, which is the development IDE for the Embedded Wizard GUIs, that is going to be supported in Windows only. And so we're going to need both environments, and then we're going to leverage a shared folder between the two in order to develop our applications and then compile them specific to the i.MX 8M+ architecture. And then we'll be able to run those executables, the graphics demo, on our hardware, our target hardware. So let's first get the Embedded Wizard Studio IDE. We can do that by accessing this the URL here and then registering yourself and downloading that IDE. Note that Embedded Wizard is not an open source graphics stack, so this is something that is proprietary. You will have to pay a license in order to get access to this stuff. However, there is a free edition, and you're able to evaluate this freely. You'll just have to pay for the license in order to deploy it in a production system. So go ahead and register yourself here and download Embedded Wizard Studio, and that is going to look like this. So once we have this on our Windows host, then we can also go download the development package required for the phyCORE-i.MX 8M+ specifically. Now this was put together by the folks over at Embedded Wizard, and we'll need this to realize our graphics on that particular platform. A handy link for that we can grab from our guide, and then here it is. It's just a zip file. We'll go ahead and save it to my downloads directory on my Windows host, and then we'll go ahead and unzip that 7-zip. There we have it. Okay, so now that we have that, we'll hop over to our Linux host, get that set up. Recall in previous video we've already set up our BSP, and we have some components there already built. We've also gone ahead and installed the Yocto SDK here. And so we're going to leverage both of these things, specifically the Yocto SDK. We won't have to actually build anything using Yocto here in order to realize and evaluate Embedded Wizard. Ideally, once you have a GUI application completely developed, fleshed out, you would then commit that to a meta layer and create a recipe such that it's built into your image by default in the context of production software. So in this case, this is very development focused. We're going to use that Yocto SDK. We're going to have to source the Yocto SDK. So if you recall from previous episodes, that is going to be this command if you installed it in the default location. Once we do that, we're going to have some handy environment variables here that we can always double check just to make sure that our environment source. So this CC variable, I believe this stands for cross compile. That will point to the GCC compiler provided in the SDK, and we can see that this is specific to the 64-bit ARM architecture, which our i.MX 8M+ is. So go ahead and source your Yocto SDK environment, and we are good to go on that front. Now, in order to connect up this development package that we unpacked on the host to our Linux virtual machine, we're going to have to, and these are steps that are specific to VirtualBox, so if you're working with VMware Workstation, this will look a little different, but we can go into Devices, Shared Folders, and in here we can go ahead and add folder path. We'll select on our host, a Windows host, we're going to go to Downloads, select that environment, or that folder, and then we're going to go ahead and mount this to any location would be okay. I'm going to use mount HFS, host file system. We're going to auto mount that. Let's hit OK. Now, in my Linux host, I should be able to confirm that we have this mounted here at mount HFS. Let's just go navigate into there real quick and see what's going on. Looks like we have all these files, and these should match what I see on my host. And it looks good. We can navigate into the master demo directory here in our development package. And here we will find a executable. This is actually already built and ready to run. We can even double check that here with the file command. And we can see that this is a 64-bit binary targeting the ARM 64-bit architecture. So we could actually go ahead and run this directly on our hardware. It's ready to go. So let's pull up our development kit, double check our IP address. Looks like it's 172.22.30.143. Go ahead and grab that. Got my clipboard. Navigate back to our Linux host environment, and we can SCP this file like so to root at the IP address, and we'll just go ahead and send that to the home directory. Perfect. And now on our hardware, we can go ahead and confirm that that binary appeared, and we can go ahead and run it like this. There we go. There we have it. That is the out-of-the-box Embedded Wizard demo. This is kind of a superset of a bunch of demos. So we can go ahead and explore some of those. There's like some kind of cool wave generator. We can go ahead and explore those, and we can also take a look at the source code for all those individual widget GUIs, demos, I believe that's what they're called, widget demos. They're all going to explore like different aspects of Embedded Wizard, and so you can study that source code to help you develop your own applications. For our purposes, we're going to go ahead and kill that process, and we're going to get into creating a custom GUI just for exploring what this experience looks like. So let's head over to Embedded Wizard, open up Project Open. We're going to open one of the provided examples provided in that development package. We can navigate into examples, here 1280-800, that is the display resolution of the PB8010. I'm going to go ahead and click that, and then we have a number of demos here. All of these were included in that out-of-the-box demo we just showcased. Let's navigate into Hello World and open this .ewp Embedded Wizard project file. Double click that. Now with our project open, we can actually go ahead and evaluate this on our host directly here, very conveniently with this play button. And this Hello World is a very basic interactive. It'll move this graphic around depending on where you touch. Let's go ahead and try running this on our target hardware. So in order to do that, we're going to go here and hit build this profile. What that does is going to generate a bunch of C code using what we develop here in the studio. A lot of this is click and drag with widgets and things like that, but there is code written in the Cora coding language. Cora is specific to Embedded Wizard. Once we generate our code from Cora, then we will go and compile that generated code using the Yocto SDK, providing us our executable, and then we can run that on the hardware. So now that I've hit build this profile, do it again for good measure. Now we can navigate into our mounted development package, navigate into applications, or application, and then project. And here, we can just go ahead, as long as we have our Yocto SDK source, we can go ahead and just run make. Once make completes, then we can actually leverage this target IP.txt file, and we can supply our IP address for the target and leverage some capabilities provided in the make file. 22.30.143. Go ahead and provision that IP address there, and now we can actually run make install now to go ahead and install and run this. Now if I flip over to my hardware, there we are, and it should have that expected functionality. Perfect. Now let's go ahead and modify that Hello World demo. First thing I'm going to do is delete some of these text boxes, just go a little more space. And then we're going to navigate out of, in the templates and browsers window, we're going to navigate over to the widgets tab. We can just click and drag a toggle button right here in the UI. Now, Is this the toggle button I'd like? Let's go ahead and evaluate this on the host. Let me just see how that behaves. Okay, I like that. We could go ahead and modify some of the colors and some of the properties of this guy over here in this inspector window, I believe it's called. But we're going to leave everything at its default there. Let's connect this button up to our GPIO. And how do we go ahead and do that? We do that by navigating over to the application unit tab, and we're going to add a device interface. The device class is very generically named here. I'm going to go ahead, didn't mean to double click it. We're going to go ahead and right click it and rename it to LED class. And with that set, we're going to navigate into there. And I'd like to just get rid of all this stuff, all this default stuff. We're going to define it ourselves. And now we're going to need a property object. This is going to represent the state of the toggle button in our GUI. And we only really want to set that property. We don't really care. We're not going to have other aspects of our GUI depend on the state of that button. We just need the button to be set or not set. And so we're going to go ahead and get rid of the onGet property. And thus we're set with the property and onSet property. Real quick too, int32, that is the property type. I think the toggle button makes more sense as a Boolean, with checked or unchecked, true or false, so like my name. And so we're going to go ahead and single click that, go over here to the inspector window and change the type, the variable type for that to bool. Looks good. And finally, we're going to rename this to reflect what the purpose of that toggle button is. And we're just going to call that LED state. The toggle button will effectively be the LED state. And we can see too that changed the onset LED state function, I believe. I believe that's what these are called. There's a lot of very specific language to the embedded wizard ecosystem, so if I mess it up, please forgive me. I'm not an embedded wizard expert. Just here to help out best I can. So the onset LED state, this function is essentially going to be called whenever that toggle button changes state. And I have some code prepared off screen that will populate here. And it's going to look like that. For the most part, it's some default Cora code, which I'm not going to get into too far in this video, but we can see that depending on the state of the toggle button, we're going to be calling it LED on or LED off function. So let's go ahead and implement those. We're going to need to go over to our Cora tab here in the templates browsers window and drag and drop two method objects. And the first one we're going to call LED state or LED on, this first function. And the second one we'll call LED off. Now, when I double click this guy, I'll also get this code here. Let's populate the code I have prepared for that. Now, this is some interesting stuff going on here. You may think that there's some violations with regards to your typical programming conventions. I have a dummy variable here that I don't intend to use. Now, I did find that it was necessary to declare a dummy variable here, and you would get like these compile errors otherwise. I'm not sure what's going on with that, but this is something I found I had to set, and I believe it's also reflected in the Embedded Wizard documentation. The key function here, native, this is going to call native code. And so LED on, this essentially will be native C code that could be written and run directly on the phyCORE-i.MX 8M+. The onset LED state will call one of these functions depending on the state of the toggle button, and then that will correspondingly call native C code that toggles the GPIO directly. So let's go ahead and also implement that for LED off, and we'll take a look at how the native code is written as well here in just a bit. Before we move on, there is another step here, and it's going to be a little bit to figure out. You'll have to double click this little header here. Double click that, and we have a few things. We're going to want to change the type here to void, because once we change the state of the LED, we won't really care. I mean, if you really want to go extra mile, we could double check that the LED was actually set as a return. But here we're just going to do a very simple style. We're going to have this method or this function return nothing. And we're also going to go ahead and delete the argument for this function. We're not going to pass any arguments to the native code. And then we're going to repeat that for LED off. And we should be good there. So now we can go ahead and write our native code itself. Where do we do that? We go back to the unit application and we go to our inline object. Here's where we can put our native code, and I have some of that here prepared off screen again. Now, what did I just populate? Essentially, this is pretty much just GPIOD C code. This may look familiar from a previous video in the series. We're declaring which GPIO we're targeting there on the expansion connector on the development kit. We have a helper function request our GPIO, and then we have a function for toggling it. And in this case, I've also just defined LED off and LED on, which are the native functions that are going to be called from the toggle button handler. And those will correspondingly run toggle LED. This is probably could make this a little cleaner, but I just threw it together. So now our inline code is set. What do we do next? Now we can connect that LED class object to our toggle button. So we have this. We go over to our application tab. Oop, not that. Don't double click that. There's a lot going on. That's like the internal implementation of the toggle button. We're going to single click our toggle button and navigate to the outlet section. And that is right here. Here we can go ahead and locate the device.led state that we just configured. Now, when I click this toggle button, it should call these two functions depending on the state. We can then go ahead and build this profile. We're going to generate our C code again, navigate over to the Yocto SDK, and before we can run make, note that I did add native code with a GPIOD library, libgpIOD added, so we're going to actually have to modify the make file here in order to find that library within our Yocto SDK. And so we could do that down here on around line 93, libs. We're going to add GPIOD to this list. Gotta make it look clean. There we go. All right, now we can run make. Now it's going to complain about those, but I think it would complain even more if they weren't there at all. So I don't remember. Anyway, look that up and let me know in the comments below. We're going to run make install. Now if we hop over to our hardware, we have an issue here. So we can see here that file is already busy. We're going to have to make sure to stop that. The way I do that here, we can go ahead and do a PS for embedded. Oop. Looks like the when you run make install, it kicks it off here out of the temp directory. I think we'll have to do a kill all on that real quick. There we go. Now the embedded wizard GUI went away. Now we can run make install. Hop back over to the hardware, and now we have a toggle button, and it should toggle the LED.